You type a prompt, and seconds later, an impeccably formatted university syllabus appears on your screen. The tone is authoritative, the structure is perfect, and the academic citations look entirely legitimate. But if you try to look up that specific journal article, you will find it does not exist. When highly educated professionals accept these fabricated citations as truth, it is usually because they are operating under an incorrect mental model, treating the interface as if it were a factual database. The system does not actually know the answer it just provided. It has no repository of facts, no memory of historical events, no concept of truth or falsehood. To predict when an AI will succeed and when it will hallucinate, we have to look at the absolute mechanical constraints governing how these tools generate text. Every modern large language model operates on a single governing axiom. It is a statistical next token predictor operating on a massive scale. This process starts with tokens, variable-length mathematical chunks. While a common word like the might be a single block, a specialized term like mitosis is sliced into pieces like mit and osis, so the system can process them. Given the prompt you typed, the model scans the patterns it learned from its training data. It assigns a statistical probability to every possible chunk of text that could follow and drops the most likely token into place. Whether the model is drafting a syllabus or inventing a citation, it is using the same underlying math, matching statistical patterns found in the trillions of words it was trained on. Because the model constructs its answers via word-by-word probabilities rather than factual retrieval, using it as a lookup table leads to inevitable errors. Transforming raw internet text into a conversational chat interface involves 3 distinct manufacturing phases. In Phase 1, pre-training, the model ingests trillions of words. It acts like a student reading every book in a library exactly once, learning the grammar and statistical relationships between concepts, but without a grounding in what is actually true. This creates a hard limit. The model's knowledge is entirely frozen at its training cutoff date. It has no way to learn new information or adjust its worldview once this phase ends. Phase 2, fine-tuning, is where human trainers use examples to teach the model how to follow direct instructions and format responses for a professional audience. Finally, in Phase 3, the model is taught to prefer responses that appear helpful and harmless. This creates the interface we see, a tool that mimics the caution of a human assistant. But because factual learning stopped after Phase 1, that helpfulness is a learned stylistic behavior, not a sign of active reasoning intelligence. The 2 seconds between hitting send and seeing an answer involve an invisible 6-step mechanical pipeline. In Step 2, context assembly, the system loads your prompt and previous messages into a fixed-size working memory window. This window is the only thing the AI can see. If a professor attempts to plan an entire semester in one long chat, earlier instructions eventually get pushed out of the box and are permanently forgotten. In Steps 3 and 4, the model doesn't just calculate a single correct answer. Instead, it samples from a statistical distribution of plausible tokens. This is controlled by a parameter called temperature. By adding randomness to the sampling, the system ensures that asking the same question twice will yield different answers by design. With a memory that is strictly temporary and outputs governed by mathematical randomness, the tool is not built for deterministic, repeatable results. Understanding these mechanics allows us to dismantle the 6 most common professional myths about AI. Because it predicts tokens rather than retrieving files, the model is not a database or a search engine. It has no native access to the live internet or factual lookup tables. It is not a calculator. It approximates arithmetic based on text patterns, which makes it unreliable for tasks like graining or data analysis. It is not conscious. When an AI expresses empathy for a student's struggle, it is simply replicating statistical patterns of human language without any actual understanding. Perhaps the most dangerous misconception is that the model knows its own limits. In reality, a confidently written falsehood is just as easy for a next token predictor to generate as a fact. Hallucinations are an inescapable feature of the statistical prediction process. Educators must actively manage them rather than waiting for them to be fixed. Treat the AI as a brilliant amnesiac intern. It is brilliant at structural tasks like drafting syllabi.
But it's a severe amnesiac, resetting its memory every conversation, blind to new research. It's also eager to please, fabricating confident answers rather than admitting ignorance. Use the intern for drafting and formatting, but retain strict executive authority over facts, arithmetic, and citations. To move from passive trust to active verification, run a baseline stress test. Select a factual question from your field where you know the answer. Input that prompt into 5 AI platforms concurrently. Categorize each output as a hit, near miss, or hallucination. Observing these error patterns firsthand calibrates your expectations, letting you use the AI as a starting point rather than an authoritative final product.